Good afternoon, Saturday, March 6th, May 6th, 2023. Bright, sunny, clear. Contrary to the weather report of yesterday, which was mistaken. Why are there economists to make the weatherman look good? So, from reading this Einstein's out of my later years, we completed a summary after a conclusion of the chapter on physics and reality. And in it, Einstein really kind of wrapped up what were his requirements of a theory that's his general relativity and his special relativity. And a very not too generous reading is able to see that Einstein has stated again that it was always the case that space is absolute while that motion is relative, and about the mass energy equivalence that it's a thing, and with regards to the rotational and space contraction, and that's different from length and space contraction, and about the Galilean and the Newtonian and the classical laws, classical kinetics, and about what is the higher order of the kinematics, and that includes the rotational besides the linear. It's a thing. And so it really goes a long way to help explain that the metric of the Riemann tensor, and is about the definition of that for essentially gravity wells, where in the space-time that a gravity well embodies the study of regions that are largely free of contents, yet that have several large things that orbit each other, like the solar system. And with regards to how that's a thing and why it works, that is still yet so that there are relativistic dynamics in all things. There's a space contraction in all things. It's a real phenomenon. And now this is more my theory, and Einstein would let that out, and because his next chapter is on the fundamental theoretical physics, we had a lot of reading from Einstein about the fundamental elements, and last time I started with Heisenberg explaining a little bit from antiquity that our theory of atomism, of course, is ancient, and that he then begins up to the modern atomic theory. So we might read a few pages from Heisenberg's book here about Boyle and Lavoisier and their studies of gases and discovery of oxygen and formulation of the species of elements. And Richter, Gassendi, law of constant proportions was then raised by Dalton to the status of a fundamental law of chemistry. In 1792, the German Richter discovered that chemical elements always combine in chemical compounds in definite quantitative proportions. And we call that the stoichiometric. It is not possible for just any arbitrary quantity of hydrogen to combine with just any arbitrary quantity of oxygen to form water. Hydrogen and oxygen must always combine in the proportion of 1 to 8 to form water. Otherwise, there remains an unconverted residue of hydrogen or oxygen. This law of constant proportions was then raised by Dalton to the status of a fundamental law of chemistry, and within a fairly short time, it led to the union of chemistry with atomic theory. These days, we also talk about the molecular chemistry, that anything that's extra local is as with regards to the molecular chemistry, or that of resonances about their waves, but that molecular chemistry and similarly molecular physics involves also when there are differences in properties via an atom and its organization, a crystallographic lattice, according to not just its state of matter, but its fundamental form and organism with regards to all the other processes that result from any kind of physical interaction, which again is this theory of some potentials adding up to what is the impulse anywhere and everywhere from each origin, according to the principle of least action. Those macroscopic theories or molecular theories are a big deal and a thing, and there are lots of different works that help explain why these are so. We can talk about Brandon Speakman. It's another book that I don't have here, but I have elsewhere, that helps explain what and how and why that science has discovered this is like so. And it's similarly with the differences between thermo first law and thermo second law, for example. It's similar in the differences in kinetics between heat and the contributions of kinetics to heat, and whether, for example, that there's more to heat than just kinetics. Well, that has to do with structure, it has to do with lots of things. But the kinetics are its measure, and then there's vibration and the resonance of harmonic actions and sympathetic things, and then there's above vibrations and these resonances, and also then displacement and motion. Just as examples of that there are bodies, and that they are the collection of all their material points also, and that then for Einstein that they're rigid bodies, and that there are kinetics and kinematics. And then for chemistry here, for atomic theory, it's that these bodies are arbitrarily small, the atoms, and arbitrarily large, the number of atoms per mole, that 9.022 times 10 to the 23rd, or approximately Avogadro's number, over time grows. This is something that people should be familiar with at NIST, National Institute of Standards Technology, CODATA, from the Particle Data Group, that collects all the massive high-energy accelerators experiments from all over the world. Over time, finds that the smallest fundamental physical constants decrease. Not get more precise, but get more precise and decrease. So for something that otherwise it says that, we measured the value of the electron, it's called the Millikan oil drop experiment, where charged oil droplets were determined by observing how they fall under gravity, their mass, and this kind of thing. Well, that's a process of discretization, and it's in a process, it regards to the configuration of the experiment. And it ends up being a thing that then all this stuff happens in terms of the aggregates of them, the surfaces of them. So atomic theory is at once what can affect things on the atomic level by cutting them, basically, that is transatomic. That these are the kinds of things that make for why science is so profound and fundamental physics is so fundamental, and that foundations is fundamental. Dalton stated this law of constant proportions in a more precise form and gave it a geometrical interpretation. It is this very geometrical interpretation that is of paramount importance. We shall try to make it more intelligible by an example. When hydrogen combines with oxygen, form water, we must visualize this process as a mutual combination of the smallest particles, atoms, of both elements in a higher, more complex unit, a water molecule, according to our modern terminology. We are now in a position to visualize a molecule as a geometrical structure composed of individual atoms, and a water molecule as a structure composed of 2 hydrogen atoms and 1 oxygen atom. And that their bond angles are like so, and that their orbitals feel like so. There's a great book, this Inorganic Chemistry, or the Geochemistry, that really helps give a good solid description of the model of orbitals of the electrons. Then that with regards to the folding of molecules and the states that they have with their bonds and their angles, usually with regards to what's called active sites and their reactions in chemistry, and how catalysts work and how enzymes work with regards to proteins and all these kinds of things, the cleaving and the catalysis and the usual rates of reactions and sites of reactions, the active sites, that these are usual things. That Heisenberg continues, this view makes the law of multiple portions directly understandable. The compound which we call water is thus characterized by the 1 to 2 ratio of oxygen and hydrogen atoms. This theory of Dalton, advanced in 1803, of atoms combining in molecules in a manner capable of geometric illustration, was further developed and raised within a few years to the status of an established scientific postulate. As early as 1811, Avogadro announced a daring hypothesis by which he laid the cornerstone of what we know today as the chemical theory of atoms. He maintained that at the same temperature and pressure, equal volumes of all gases contain the same number of molecules. Although this hypothesis was still in need of an experimental proof, it soon turned out to be the clue to the determination of atomic weights. And it also provided a solid permanent foundation for Dalton's atomic theory. So yeah, today we probably consider that more in terms of the mass of these quantities, not their weights so much. That in one atomic mass unit is bare hydrogens, say, but it's kind of like one astronomical unit, or one mass of the sun's unit, or something like that, in terms of the normalization of these things. Heisenberg, if the number of atoms or molecules containing a specific quantity of gas is known, the decomposition of an individual molecule can be stated exactly. For instance, whether a water molecule actually consists of one oxygen atom and two hydrogen atoms. And then that gets into that, for example, often gases aren't so much single atoms as ions, or the chargeless assembly, like that hydrogen mostly floats around as H2. They're pairs, or this kind of thing. Thus, the way was paid for a quantitative determination of the weight or mass ratios of atoms. Although the absolute number of atoms present at any one time was not yet known, it was known for certainty that at the same temperature and pressure, the number of molecules containing equal volumes of gases was the same. This was sufficient since it furnished information concerning the mass ratios of atoms and molecules. Not much later, the Swedish scientist Berzelius determined the atomic weights of a great many molecules and succeeded in developing very definite theories about the way in which molecules are built from individual atoms. Berzelius also studied the nature of the forces binding atoms together in molecules. It was he who introduced the notion of valency in connection with the force binding an atom of one element to an atom of another. In studying this force, he came to the conclusion that it must be of electrical nature. Organization in the kinetic can begin as small as otherwise, but it's the electrical bonds that are so strong, otherwise, where the asymptotic freedom of something like a fall gravity makes it fall out the strong nuclear force, otherwise that it's bonds, and it's also kinetic in the sense that usual things that cleave and what are built upon the action that results that there's ionizing things that affect one part of the active site, they affect kinetic things with regards to the other. So the theory then of electron orbitals and pretty much the idea that protons define the atomic number vis-a-vis the atomic mass, because protons and neutrons are each about the same mass, or that the mass of a neutron is almost defined as the mass of a proton plus that of an electron. That's a little bit different. Has that, then there's the questions of the isotopes. Where basically chemically anything is only defined by its atomic number, because that many protons makes to orbit that many electrons in something that's not ionized or having an electric charge, the particle. So these days it's very well known that's so, but only 150 some years ago it was rather new. The status of atomic theory about 120 years ago can be summed up as follows. So this was about 220 years ago. It was known that the prodigious number of chemical compounds could be reduced to a relatively small number of chemical elements, a great many, though by far not all of which are known. The IUPAC is the International Union of Practicing Applied Chemists, or something like that. So IUPAC or IUPAC has basically a nomenclature for any chemical compound, if I recall correctly. And so there's a normal way to read out any chemical compound as of what its formation is, as of its form. And it's an important thing to learn because there are many, many, many more compounds than there are usual normal words in the natural language called English. And so it ends up that the normal names for these things, normalized names for these things, some are very, very long. It just kind of represents the content of one of these atoms and their molecules. One of these molecules, if you'll excuse me. So that's the thing. Some more well-known compounds have shorter names that also often follow a nomenclature. That the enes, anes, ines, and wines are examples of all sorts of things. That the alls and eights and eights and eats and such are all sorts of, according to the suffixes of thing, that the dihydrogen monoxide is water, H2O, or 2HO. For an example, that chemistry is very specific about its contents. The mass ratios of the atoms were known fairly accurately. One oxygen atom was roughly 16 times, and a nitrogen atom roughly 14 times heavier than a hydrogen atom. Nothing at all was known about the absolute size of atoms or the order of magnitude of their number within a given volume of space. So as far as accurate knowledge was concerned, an atom might still, as Democritus had believed, be approximately the same size as one of the motes dancing in a sunbeam, or infinitely smaller. Just as little was known about the shape of atoms or about the forces operating between them. As to the latter question, nothing but extremely hypothetical conjectures was possible. Furthermore, there was known that chemically the atoms must be the ultimate building blocks of matter, not including nuclear transmutation, which changes the atomic numbers of atoms or their molecules, or their atoms, resulting they just have different chemical properties. But furthermore, although it was known that chemically the atoms must be the ultimate building blocks of matter, in other words, the smallest units demonstrable by chemical means and methods, no one knew whether or not these chemical atoms might be capable of being further subdivided and transmuted into each other by the application of other methods. A discovery from which Prout was the first to draw conclusions in 1815 actually spoke against the theory of the absolute indivisibility of atoms. Prout, or Prout, P-R-U-T, based his deductions on the fact that the atomic weights known in those days, that these were mainly only those of the lighter elements, were nearly integral multiples of the atomic weight of hydrogen. So he had a building block of those. There are many models of the nuclear contents. And these include, for example, that the nucleus is centered in the middle of an atom whose radius is defined mostly the space that its orbitals of electrons fill as shells, and the atom is mostly space. Whereas at the same time, there are some models that, like atoms and their organization in molecules, are surfaces and essentially one surface, one body. Now that's not the usual, because otherwise usual atomic models are like the billiard ball nucleus, the pudding. So that's more of a, like, I suppose, a pudding model than a billiard ball model. These are these kinds of examples of models. That the models advise us for phenomenological access and our means in grasping the sensibility for the fungibility and tractability of the models, work for how they build up these theories of their fundamental objects, their elementary objects, their independent objects, those models, their interactions, lack thereof. The hypothesis, which postulated the existence of nearly 100 different elements, had always been regarded as rather difficult to accept, for if we really believe in homogeneity in nature, we must obviously prefer the number of basic elements to be considerably smaller. If more multitudinous. So you might think of smaller, but there's also the notion of smaller means less multitudinous. But again, this is this Schaffer's laser idea for Occam's razor. Occam's razor being, do not necessarily multiply things which don't exist, and Schaffer's lasers, ... fundamental entities. But there's definitely something to be said for the paucity of theory, but it needs to be simple as it can be, no simpler, whereas at the same time it can't be overly simple. About the elements, and they have like the usual periodic table of elements is one of the greatest things that everybody ever finds when they're learning about the world and physics. And when they find the periodic table of elements and how it's so organized with the filling of the electron orbitals, I forget, 1s1, 2s1, the filling of the sp and d orbitals and and outwards. And then the presence of the halogens and the noble gases on the other side, and all these things to do with then under lanthanum. Then there's the lanthides and let's see, the lanthides and the other ones under those nuclear species up above. Then there's some 200 plus known elements today. Many of the higher ones only really built in the laboratory apparatus by the enrichment of atoms with nuclear methods, and these are known usually to have very, very short half-lives, where half-life is basically the time that a given quantity of a substance will transmute, that all atomic species pretty much have half-lives of various lengths, from milliseconds to millions of years, but mostly less, and that there's the usual notion of the formation of the heavy elements in the solar furnace, or that the elements kind of go towards the center, where the center of the stability is iron, some have. And then there's that, there is the notion that there's an island of stability up above, yet the elements that have just been found, like ununium and these later elements, maybe I'm thinking of the weights, not the numbers, if there's only a couple hundred so far, or less than that, where the latest elements are named by the atomic number, and then they're later given a name representing their location of discovery, or who theorized and presented their discovery as existence in terms of the elements. Then that, of course, all the existing elements kind of have names that were already applied to them. Like mercury, it's elemental, and gold, or Au for gold, Fe for iron, the ferrous. That the periodic table of elements is a really great thing, and it gives somebody who's curious about these things, about all kinds of what it is. Then there's all kinds of states and matter and organization is another whole huge thing. The carbon comes in many forms, and well, there's the carbon-based life forms have the most all biological animate things on Earth are carbon-based. Then there's live rust or something, what is that? Or there's things that live in steam vents, they don't have oxygen as their usual milieu, or they don't have photosynthetic complexes or something like that, with regards to the generation of energy and the conversion of energy. There's, though, that all these different elemental forms, besides their chemical composition, also have their crystallographic, and their existence as metals or as substances, and different forms which make for any kind of interaction zones, the zones in the media of these kinds of things. A new era in atomic theory was introduced by Faraday, who combined atomic theory with the theory of electricity. Atomic theory is indebted to him for the formulation of a law of prime importance. In chemical changes induced electrically by electrolysis, there is always a relationship between the matter transformed and a definite quantity of electricity. Moreover, Faraday discovered that the masses of the substances transformed by a certain definite quantity of electricity are related to so-called equivalent weights, and thus in the simplest cases those of univalent substances to the atomic weights of the substances concerned. This discovery indicated that electricity, too, possessed an atomic structure of such nature that each atom or each molecule of a chemical compound was always associated with one or more atoms of electricity, even though in some manner then still unknown. So this is expressing this law of proportion. Then at the study in the ultimately degenerate, or the quasi, the pseudo, the deconstructionist account, that they're atoms, and then there's subatomic structure. And then there's also these discrete notions. This discrete relation here is otherwise only as an exercise in discretization or exercise in quantization, but it reflects over all these ratios of the substances of one and the substances of the other. But this is a pretty nice fact about Faraday, where he explains that this relationship exists. This was pointed out by Weber as early as 1848. Explains logically why the same quantity of electricity was always associated with the same quantity, in other words, the same number of atoms of a substance. Today, the mole, M-O-L, also written mole, M-O-L-E, the mole, and the gram atom, Gramme-atom, gram atom, are customarily employed as basic mass units. 1 mole of any substance is that quantity which weighs as many grams as the numerical value